Hello viewers, in continuation of my lecture on phase equilibrium, I'll go for the application of phase rule. But before starting that, let me explain what we did in my last lecture. We know that phase rule equation is a simple equation, and we looked at the derivation of that equation. I also gave you a hint about how to apply this equation to real systems. Today, I'll start with the application of phase rule to one component systems. This is the way we can approach, because phase diagrams can be highly complicated depending on the type of systems that we handle. So, we can start with the phase diagram of water system. Reason being, we are familiar with water. Water is a wonderful liquid. It's a colorless, tasteless, odorless liquid and is calorie free. It also can defy gravity, and it is probably the only substance that exists on this planet Earth in all the three states, and we are familiar with these three states: solid ice, liquid water, and gaseous state, that is water vapor. Water is life. That is why it is very interesting to study the phase diagram of water, and there are various reasons for it. Water system is a one component system. That means C is equal to 1. There are three one phase equilibria. That means our system can work and exist as ice alone. It can be in the liquid state, water, and it can be water vapor alone. Similarly, there are three two phase equilibria: ice in equilibrium with liquid water in equilibrium with water vapor, and ice in equilibrium with water vapor. There is one three phase equilibrium possible, in which all the three phases exist together in equilibrium: ice in equilibrium with liquid water, in equilibrium with water vapor. Let us look at the phase diagram of water system. One phase equilibrium, as I mentioned earlier: ice, water, water vapor. We can apply phase rule to this system. One component system in one phase, that means number of degrees of freedom is 2. The system is said to be bivariant, that is F is equal to 2, let me stress, and the diagram is here. In one of my earlier lectures, I had told you what will be the nature of water phase diagram, and we had predicted that it will have three areas: areas of existence of ice in the stable form, the pressure and temperature conditions, and another area for liquid water, and the third area for water vapor. What we mean by bivariant system? We can change pressure at any given temperature, as well as at any given pressure it is possible for us to change the temperature without changing the number of phases. This confines and conforms to the definition of the number of degrees of freedom, that it is the number of variables that can be arbitrarily fixed without changing the number of phases present in the system. Let us move forward and take up the two phase equilibrium possible in this system: ice in equilibrium with water vapor, ice in equilibrium with water, and water in equilibrium with water vapor. Apply phase rule to it. F is equal to 1 minus 2 plus 2 equal to 1. That means the system is univariant when there are two phases in equilibrium. F is equal to 1, and the diagram is here. We have a two phase equilibrium represented by curve OA, which is solid ice in equilibrium with water vapor, and then we have OB, in which ice is in equilibrium with liquid water, and OC, the equilibrium between water and water vapor. The system is univariant. That means we have the liberty to fix only one of the variables, the other one becomes automatically fixed. Look at this. If we fix the pressure as 10 atmospheres, then the temperature is definitely fixed here. Similarly, if I fix the temperature, the pressure becomes automatically fixed. This diagram needs a bit of elaboration. The best thing is to start with the point A. As we move along this line, this gives us the pressure and temperature combinations in which the solid ice is in equilibrium with water vapor. We know under which conditions solid and vapor are in equilibrium. Yes, it is sublimation, and therefore this curve is called the sublimation curve. When we reach point O, we reach an intersection at which we get two lines OB and OC, which form the boundaries for the region in which water comes into stability. The curve OB gives us the equilibrium between ice and liquid water. The process in which a solid gets converted into liquid is called fusion or melting. Therefore, OB can be called a fusion curve or the melting point curve. Similarly, if we move along the curve OC, this gives us the temperature and pressure conditions under which water is in equilibrium with water vapor. Conversion of liquid into vapor is happening at the boiling point, and therefore the curve can be called the boiling point curve, or we know the definition of boiling point. Boiling point is the temperature at which its vapor pressure becomes equal to the atmospheric pressure or the confining pressure. Therefore, this curve can also be called the vapor pressure curve. Three-phase equilibrium. There is one possibility, as we have seen. All the three phases of water can coexist in equilibrium, and if you apply phase rule equation to it, we get the number of degrees of freedom to be 0, and the system becomes invariant system. The phase diagram is here. This point of intersection of the three curves is the point at which ice, water and water vapor are in equilibrium, and therefore it is called the triple point. You can also call it the invariant point because F is equal to 0. And since there is no degree of freedom with us, we can neither change pressure nor temperature because there is no degree of freedom available to us, which means the system fixes both the temperature and the pressure. That is why this is taken as the reference for devising the Kelvin scale of temperature. Now, moving forward, we had talked about metastable equilibrium. If we take a clean sample of water, dust free, in a container that is clean and smooth, and start cooling it, we can take the temperature of water down to -5 degrees centigrade without any solid ice appearing. We said that is a condition of metastable equilibrium, and we can preserve water in the liquid state at -5 degrees centigrade as long as we want, provided we do not disturb it. Seeding or stirring will immediately change it to the solid state, and the temperature rises to 0 degrees centigrade. And even this can be shown in the phase diagram, and we have curve OA prime, though very small part of it can be traced of the metastable equilibrium. Nevertheless, it can be clearly seen there, and the curve OA prime that we have drawn is actually an extension of the curve OC below O up to A prime. That is the vapor pressure curve of water extending below the triple point. As we move along the curve OC, we reach a point C at which the curve abruptly ends, and we know why. Because we reach a point at which the liquid and the vapor become indistinguishable. Yes, it is the critical point. We have defined critical temperature earlier. Critical temperature is the temperature above which a gas cannot be liquefied, and that is exactly what happens here. So, there comes a restriction on the system, because along the line OC, number of degrees of freedom was 1, it was a univariant system, but when we reach the point C, the restriction that comes into being is that the liquid and the gas, that means in this case vapor, become indistinguishable, and because of that whatever degree of freedom that we had, we lose it and the system becomes an invariant system. And that is why point C is the critical point, and that happens to be now the characteristic of the system. The temperature and the pressures for water system are given here, and they are fixed. If you go beyond the critical point, that means if the pressure is above the critical pressure and the temperature is above the critical temperature, we reach the region in which the two, the gas and the liquid, become indistinguishable, they become one. There is a smooth transition at critical point from liquid to vapor and vapor to liquid, and we have an interesting region with several applications coming in called the supercritical fluid region. I had mentioned that melting points and boiling points are characteristic of pure substances. Let us take water as the example. Why the melting point of ice is 0 degree centigrade and boiling point of water is 100 degree centigrade? Can they change? Look at the phase diagram. Let us start with a sample of ice at point given x. We are in a bivariant region. We can change both temperature and pressure as per phase rule, because we have 2 degrees of freedom. We can arbitrarily fix, and even after we fix the pressure at 1 atmosphere, we are left with 1 degree of freedom, so that we can move along the line without anything happening other than increasing temperature, and ultimately reach the point y, at which liquid water makes its appearance, at which it becomes a two-phase system. We lose 1 degree of freedom, and therefore at point y it becomes a univariant system with F is equal to 1. We have used this degree of freedom already in fixing the pressure, therefore the temperature cannot be other than 0 degree centigrade. That is why ice sharply melts at 0 degree centigrade, and whatever heat that we supply is utilized in the melting process, and once the ice is completely converted into liquid state, we regain our degree of freedom and we can move along the line y z. Since we have 1 degree of freedom available, temperature can change again at point z. We lose 1 degree of freedom. This is the point at which liquid water gets converted into water vapor for the first time, and it becomes a two-phase system, and we lose degree of freedom, and one of the degrees of freedom that we have utilized, and therefore the boiling continues without any changing temperature, that is 100 degree centigrade. That is why boiling point of water is always 100 degree centigrade, provided the pressure is 1 atmosphere, and melting point of ice is 0 degree centigrade, provided the pressure mentioned is 1 atmosphere. Let us look at how pressure affects the melting point of ice. We look at the line OB, which is the fusion curve or the melting point curve. The curve OB has a negative slope, which clearly tells us that as the pressure increases, the melting point of ice decreases. Let us see the application of phase rule in sports. Why an ice skater can zoom fast and spin easily on a ice skating rink? This question I had posed in the beginning. See here, it is possible for them to move so fast and spin. What happens actually is the weight of the skater gets concentrated on the thin blade which is in touch with the ice surface. This pressure that is exerted will melt ice to form a thin film of water, and this film of water acts as a lubricant, and thereby the skater is able to zoom fast on the surface of ice. There is another interesting process called the freeze drying. We can try to explain it using the phase diagram. We know that there are several biological specimen and pharma products which need to be dried. Let us consider our sample is somewhere here, under ambient conditions, 1 atmospheric pressure and 25 degrees centigrade. Drying the sample generally is done by heating. That means whatever water is present in the sample is driven off as water vapor. But this path is disallowed because the specimen is heat sensitive. It is not possible for us to follow this path for drying. So, what we do? Phase rule has given us a path. Instead of moving towards water to water vapor, we move in the backward direction. The sample is first frozen, and whatever water or moisture that is present in the sample slowly freezes to give small crystallites of ice. And once these crystals are detached from the specimen, you apply vacuum. And once the vacuum is applied, the pressure decreases and ultimately we cross the line which is called the sublimation curve. That means ice crystals present in the sample sublime and the sample becomes dry. Let us look at the effect of temperature on boiling point of water. Here is the phase diagram. If you look at the curve OC, it has a positive slope, which tells us that if I increase the pressure, the boiling point of water must increase. That is exactly we see boiling point of water increases with increasing pressure. We can think of explaining how a pressure cooker works. How does food gets cooked faster? This is the pressure cooker. We have a lid which is tight and a weight which releases the pressure whenever a pressure exceeds a limit. So, when you close the lid, the water vapor that is formed in a pressure cooker is not allowed to get out. The pressure inside builds up. When the pressure builds up to much in excess of 1 atmosphere, we know that the boiling point of water also increases to higher values, much more than that of 100 degrees centigrade. At higher temperature and at higher pressure, which has built up its own pressure inside the cooker, the food gets cooked faster. While in an open pan, water starts boiling at 100 degrees centigrade and temperature will never go beyond 100 degrees centigrade, and hence it takes its own time for the food to get cooked. Another interesting feature which we probably have not come across in this case is polymorphism in the case of water. We know of ice, only one ice. The occurrence of different crystalline forms of a substance is fairly common and is known as polymorphism, and water also shows several crystalline forms, and at a specified pressure there is a definite temperature called the transition point at which one form changes into another form. We are familiar with the sulfur rhombic, sulfur monoclinic transitions. The change can be reversible. In such a case it is called enantiotropic, and it can be irreversible, then it is called monotropic. Let us look at the water system at high pressure. This is a complicated part of the phase diagram of water system. It is a curiosity that made me to show you this diagram. The ice that we generally come across is ice 1, the normal ice. But if you go to pressures higher than 2000, several thousand atmospheres, there is an entirely different world in which we have several polymorphs of ice. If you look at here, we have named ice 2, ice 3, ice 5, ice 6, ice 7 and ice 8 which comes after this. And if you look at the temperature is 75 degrees centigrade, because for us ice melts at 0 degrees centigrade and water in the liquid form is the phase that we expect. But here is an ice which has a melting point above 0 degree centigrade. What we have not mentioned? We have not mentioned that we need to have the pressures as high as 22,000 atmospheres. Another interesting observation some of you might have made in this slide, that we started with 1, 2, 3 and skipped over to 5. Where is the type 4? 4 was an illusion. Its existence could not be confirmed by experiment. It happens in many cases. The discoveries are reported and then we have to withdraw it, like once the so-called polywater was announced, but then nothing is heard about it later. Let me summarize today's lecture. To start with, the application of phase rule to real systems, the starting point has to be one component system. And when it is a one component system, the best thing is to start with the phase diagram of water. And we have seen and described the phase diagram of water and how to extract information from the given phase diagram. In my next lecture, I will discuss about the phase diagrams of carbon dioxide and sulfur systems. Both are examples of one component systems, but differing from that of